the I'll give you the line, chapter, and verse of the current script. This is not to guarantee it will be the script a few days from now, but this is sort of consensus of what people believe right now. The most general picture that is sort of acknowledged is that we live in a universe that sprang from a multiverse that has existed for all time and covers all of space. And this multiverse has unknown characteristics in terms of number of dimensions and so on. But at some point, about 13.8 billion years ago, quantum fluctuation in this multiverse gave birth to our universe. Presumably in this multiverse, the same thing happens at various times in various places. So we are one of perhaps an infinite number of universes that have sprung into life and existed over an infinite period of time. Within this universe that we have, at some point, this quantum fluctuation reached size and energy density that allowed it to start expanding outward. It's the expansion of space-time into whatever number of dimensions exist in the multiverse. And we know from information we have today, looking back in time with telescopes, especially with radio telescopes, and also inferring from what we measure today, what happened in the first few microseconds of that universe existence. So before I discuss what happened in forward-going time, I want to talk about what we understand about states of matter and energy from experience here on Earth. Suppose we start off with something that on Earth is cooled down very close to absolute zero. According to quantum mechanics, we can't reach that absolute zero, but we can reach within a very tiny fraction of absolute zero. So suppose we start heating that up. As we heat it up, almost everything at that point is a solid, except for perhaps superfluid helium. In this state, there's virtually no motion between atoms or molecules. And so in most cases, what we have is a solid that's locked in rigidly because there's nothing to break the bonds between adjacent atoms or adjacent molecules. As we start heating up, we eventually reach the point where the agitation of the atoms or molecules allows the particles to move relative to each other. And we then melt the solid into a liquid. That liquid, the particles do not have enough energy to escape the van der Waals forces that hold them together, but they can move relative to each other. So they slide over each other with relatively little friction. And so we have a traditional liquid. If we keep raising the temperature, the liquid particles obtain enough energy for some to be able to break free of the surface tension of that liquid, and it evaporates. So we have a gas. If we keep on heating, that gas, once it reaches a temperature of about 3,000 degrees Kelvin, starts dissociation of the atoms. The atoms then become ions with free electrons and free positive particles. That is the state of most of the matter in the visible universe, ordinary matter that we see. We happen to live in a tiny fraction of that universe where we're not plasma, although we can produce a plasma quite readily by lighting a candle, for example. If we keep on going up in temperature, eventually the atom's nuclei starts to dissociate. And that gets us back to a state in the early stage of the universe where we had the particles broken down into the most fundamental particles. And this state has been achieved on Earth. It's a quark gluon plasma, or liquid. They call it quark gluon soup. This soup, if we keep on heating it, eventually turns, we think, into pure radiation. Although we have no way of knowing if there's another class of particles more fundamental than quarks and gluons that we would turn the quarks and gluons into. So I've been working backward from what the Big Bang did. The Big Bang started off with a burst of very, very intense radiation. The Bible says in the beginning was light, and that's exactly what the beginning of the universe was. It was too hot for any particles that we know of to exist. And so the original universe, the question was asked about why there were not other forces besides gravity. It's basically because the other forces are interactions among particles. And at that time in the history of the universe, there were no particles. Everything was pure energy. As the universe cooled down, within the first 10 minutes, the first nucleons formed. So we got the sort of lifetime supply of hydrogen, helium, lithium, and beryllium. Now, it turns out that doing the reactions, working the equations, we get exactly the right amount of hydrogen, helium, and lithium. But the amount of beryllium is different from what the first calculations showed. However, the first calculations didn't take into account how dense the universe was at that time. And so when we run the equations forward with a higher density, we get the right answer. In other words, we understand how the first light elements were formed. It took a while after that. We had to go through the first generations of stars before heavier elements like hydrogen, like carbon, nitrogen, oxygen formed. And successive generations of stars have led to more and more complex molecules or atoms all the way up to iron. But iron is a dead end in nuclear burning, and it takes something much more spectacular to fuse the heavy elements. And that something is supernova. So as the universe expanded and the first massive stars formed, the percentage of elements other than hydrogen and helium started going up. We live in the vicinity of a third or fourth generation star, our sun. And the composition of our bodies is pretty close to the composition of the sun. All the rocky material in our planet, it comes from burning of stars. Most of the elements in our body come from the burning of stars. So we are stardust. And so that sets the stage for where we are now and the observations that we make about the early universe, which determines what we think the correct theory is to go forward. So I'll stop at that point and let anybody ask whatever questions they want to ask.
Oh, we do have a question already. It says that the size of the universe is larger than can be accounted for by the matter expanding at the speed of light. But the question says that NGT suggested that for a time after the Big Bang, matter did move faster than light. Is that a correct understanding of the data?
Well, we're talking about the period of inflation. And here's what the first puzzle was when we understood the Big Bang had gone off. There are regions of the universe that we observe that are not connected within each other's light cone. In other words, they're so far apart that even since the beginning of the universe, they could not be connected by anything happening at the speed of light. Yet they look the same. They have the same scale lengths for structure and so on, which means that somehow there was something that caused some initial fluctuation in the universe to be spread out and smoothed out. And that something is, we believe, is inflation. So inflation allowed space-time to expand faster than the speed of light.
So is that a unique occurrence, Paul? Because definitely the author says nothing can move faster than the speed of light.
Well, you're correct. Nothing can move faster than the speed of light. In this case, the nothing was space-time. The laws for relativity say simply that within our space-time, nothing can move faster than the speed of light.
So I had some other questions. So forces and particles, are they, they kind of come at the same time? Does one create the other? Are they like?
Well, okay. Clearly, at the time in the early history of the universe, when there were no particles, it's immaterial whether there were forces between particles because they couldn't act on anything. So the only thing acting was gravity plus the energy of the vacuum. And later, when particles appeared, forces appeared between particles.
Yeah, I guess I'm wondering if forces are a feature of particles or if they're just like got a very deeply entwined relationship, I guess.
Well, clearly gravity acts on radiation. So the radiation does not have to appear in the form of particles. Light bends as a result of gravity. Or another way of saying it is light follows the geodesics of space-time, which mass through gravity warps.
Okay, another question in the chat. In chapter 1, Tyson discusses the 4 forces, right? Like the strong, for example. In everyday life, we can see evidence of gravity, the strong force, the sun, and electromagnetism. So how do we see the weak force that he identifies?
Well, in the present universe, the weak force basically governs the decay of radioactive elements, beta decay in particular. So when we measure the rate of radioactive decay of certain isotopes, we see the evidence of the electroweak force.
Herb, did that get the answer you wanted?
Yes, would X-rays be an example of the weak force?
I didn't understand the question.
Would X-rays be an example of the weak force?
X-rays are generally generated by fairly strong interactions. We collide something with something else. But weak beta decay is a good example.
Okay.
Paul, is inflation still progressing anywhere in the universe faster than the speed of light?
Well, we can't tell because the parts that went away faster than the speed of light, we haven't had enough time to see what's going on there.
Would you say a little bit more about the multiverse? Would you give us just a really brief kind of definition, conceptual understanding, and then could you speak to any evidence there is for the multiverse?
Well, it starts with a puzzle. When we look at the forces in our universe, the force, for example, between 2 protons, the electric force is 10 to the 49 times stronger than the gravitational force. When we look at the ratio of other forces, it turns out that in most cases, you can express a ratio in terms of fundamental constants like G, the gravitational constant, and C, the speed of light. When we look at the range of forces in our current universe, they make no sense. There's no fundamental reason why they should be that large differences. On the other hand, we can ask another question. And that question is, suppose we change the ratio by moving a decimal one place, either a tenth or a factor of 10. The answer is, we couldn't get stars, we couldn't get nuclear reactions, we couldn't get rocky planets, we couldn't get us. So the strong anthropic principle says, we are here to ask the questions because we live in a universe that allows us to be here to ask the questions, which implies that universes can have any ratio of forces that they want, except very few of them would lead to us. So the idea is that over infinite time and infinite space, every combination of universes pops up. Now, the corollary to that from a religious standpoint is God made the universe so we could exist. So it's a non-religious argument for why we live in the universe we live in. That doesn't lay to rest any serious questions, but it's basically, it's an either-or situation. Or it could be both.
So understand you right, you're saying that the probability that we would exist at random as a singular thing is vanishingly small. So
That's
there
right.
either has to be a multiverse with an infinite number of possibilities, of which we are one,
Exactly.
or there's a God that created R1.
Well, one of the arguments for the existence of God is that there had to be something that created the universe. This is a kind of a sneaky way of avoiding that impasse. It says if the multiverse always existed and is infinite in time and space, then you don't need a creator. I'm not saying that's my philosophy. I'm just saying that's what the argument is.
In the chat there, Christine has just put in a question, Paul. A friend saw me reading the text and suggested another book written on the theory of biocentrism. Can you speak to this?
Well, I'm assuming that biocentrism is the same as a strong anthropic principle, so I don't know about that book. Let me point out something else that may be surprising to people. Physicists have the luxury of never really solving the real problem. If you give them a problem, they keep simplifying the problem until they come up with something they can solve. So then they try to relate the solution they have to the real universe, which may or may not be the correct way of doing it. The point is, it's the only way they do it.
And Paul,
Quick
Nick
question, are you saying that the multiverse is a postulate or a possibility for people who choose not to postulate God or a creator?
Well, I'm not sure it's an either-or situation. The point is that one way to get the universe we live in with improbable ratios is to have many, many universes. So somewhere, here's the other interesting thing. If there's an infinite possibility, it means a universe exactly like ours existed somewhere in space and time. So we existed. Of course, we didn't know we were going to exist later.
So I've got another one. If gravity was the first force that was acting on things, how did we end up with a universe that's expanding and even accelerating?
Okay, if you blow up
Good
a
question.
balloon, the surface tension of the material of the balloon acts as gravity does to slow down the expansion. As long as the pressure you put in is greater than the surface tension, then it keeps growing. So the pressure is the pressure exerted by the collection of all virtual particles produced by that quantum fluctuation. So it blows it up once it reaches a certain level. And there may be universes that come into brief existence, but they don't have enough energy to continue expanding.
So at some point, our universe stops expanding. Is that correct?
We thought so. Recently, when they made measurements of some of the most distant galaxies and found that they were accelerating. So that's where dark energy comes in.
That's next week.
Yeah, okay.
We
Well,
got a lot on that, Dr. Cloutier. Woohoo!
Well, there's also another thing that Tyson briefly talks about. He equates dark energy and dark matter to the search for ether. Now, if you look back at the history of science, a lot of the major advances in science have come from people reaching the wrong initial conclusions or making the wrong assumptions. So The way that Einstein came up with special relativity, Michelson-Morley experiment looking for the flow of ether, Einstein, being more a mathematician than a physicist, said, if it looks like a duck and walks like a duck and sounds like a duck, assume it's a duck. So they put down on paper the equations that led to the assumption the speed of light was the same everywhere and got special relativity. And showed in the process that space and time are correlated with each other. So we've looked for dark matter, and now we're looking for dark energy. We've looked for dark matter for several decades now, and there's zero evidence of dark matter. So one possibility is it doesn't walk like a duck, it doesn't look like a duck, it doesn't sound like a duck, there may be no duck. And that our assumptions are wrong in the first place, just like the assumption of ether. The other thing that's interesting, though, which I found the most profound thing in Tyson's book, look on the page after page 12. For those of you who have the book handy, look it up. Otherwise, I'll read it to you. It says, the universe is under no obligation to make sense to you. That's the same thing as saying there's no fine print in the Bible or the Koran or the Torah or any of the other scripts that says in fine print, God guarantees that he will make everything visible to you or logical to you. God doesn't owe you an explanation, or Allah or whoever. So one of the real issues is, where do we get the idea that the universe, as complex as it is, will ever be something we can understand completely? And I'll talk about that a little bit more when we talk about life elsewhere and why aren't there interstellar travelers.
So if the theory of dark energy, because there's no evidence, turns out to be false, and that theory today explains, I assume, certain things, what are those things that then have to be explained otherwise?
Well, okay, the evidence for dark energy is that we see at the greatest distances galaxies, specifically quasars, that are dimmer than they should be. So we infer from their redshift and their dimness that they are accelerating or have accelerated in the expansion of the universe. But again, it may be false assumptions. Good example for dark matter. Vera Rubin was the discoverer of the rotation curves of galaxies that says galaxies, the stars at the outer reaches of galaxies are moving faster than they should be based on the visible mass in the stars of the galaxy. Well, there's one basic assumption that was made from the start, and that is that the galaxies are in gravitational equilibrium. When you make the assumption of equilibrium, you make an assumption that then allows you to check that observation. When it doesn't match, one possibility is you made the wrong first assumption. They're not in equilibrium. For example, almost all large galaxies have central black holes. The stars in the vicinity of black holes are moving very, very fast, nearly the speed of light. So if another star encounters those, they get whipped out and sent out of the galaxy. And we've actually identified some stars moving between galaxies that got expelled from their parent galaxy. It could be the stars, the outer reaches of these large spiral galaxies are not they're not captive of the galaxy. They're stars leaving the galaxy because of interaction with the central black hole. In that case, all the assumptions about dark matter start falling apart. Or maybe gravity doesn't act the way we think it should over very large distances. So the greatest breakthroughs in physics have come as a result of making erroneous assumptions and then trying to back those assumptions up. There's a joke about a fellow on a pile of horse manure with a shovel, digging his way down. Somebody says, "What are you doing?" He says, "There's got to be a horse in here somewhere."
Paul, would you expand a little more on gravitational equilibrium?
Okay. Let me give you a good example in the case of our solar system. We know from dynamical models of our solar system that when our solar system first formed, there must have been about 10 times as much matter in the solar system than is currently found in the planets, which means 90% of the matter in our solar system got expelled or fell into the sun. We know that we can send objects out of our solar system using planetary dynamics. At present, there are 5 man-made objects leaving the solar system. Voyager 1, Voyager 2, Pioneer 10, Pioneer 11, and the Pluto Express, New Horizons. We sent those out of the solar system, not by the rocket power that we had to get them off of Earth, but by slingshotting with gravity, bouncing them off of big planets. So in the early solar system, we lost a lot of material that's probably out there headed for other stars. We had 2 recent visitors from other star systems, one a comet and one a rocky, strange looking object. So it could be the galaxies do the same thing. They sling stars out through gravitational interaction with their central black hole.
Hey, Paul, can I ask you just some kind of rapid fire questions?
Go ahead.
These will be familiar to you. They're from, you've probably seen them from Antha and me, but
Okay.
Can we still create matter by separating quarks? The chapter talked about the force between quarks gets stronger the farther you pull them apart until they snap, and then it snaps and 2 quarks are created at each end. Can we still create matter by doing that?
Well, we think so. We're right at the edge of our ability to reach those energies with accelerators. But theoretically, that's certainly possible.
And what theories are there about why there is a matter-antimatter imbalance, which is of particular fascination to me?
Well,
that seems just really strange if you're going to have a rule that there's going to be one of each particle, and then you're going to break the rule, and that gets you the universe. Yikes.
okay. Fitch and Cronin showed that there's an asymmetry in the way certain fundamental particles interact. That can produce, it's a symmetry breaking process that can produce an excess of one particle or the other. As to why it happened, who knows?
Is that really about all we know about it? Just that it does happen and that it breaks rules when it does?
Well, okay. If we believe that the universe is out of the multiverse, can start with slightly different conditions due to quantum mechanics uncertainty, then some will have reactions that lead to an excess of matter. Some will have the possibility or probability of producing antimatter. Except matter antimatter is out of the holder, because we are made of what we call matter. The other stuff is antimatter. It could be we're actually antimatter in some universes, and the stuff that's missing is matter. But quantum mechanics says there will be fluctuations in both directions. You'll never get exactly the same answer according to quantum mechanics. So that could be the best or the easiest explanation.
So Paul, if matter and antimatter are at a slight imbalance, and I think the book says it's like 1,000,000,001 versus 1,000,000,000.
Right.
Is there a charge imbalance, or why isn't there a charge imbalance as well?
Well, in terms of matter or antimatter, every particle has its sort of mirror image. So to have a charge imbalance, you'd have to have either more protons than electrons, or antiprotons and anti-electrons. So there's no evidence that there is a charge imbalance. The evidence is that matter, what we call matter, predominates over what we call antimatter. So it's not that more positrons were produced than electrons, it's or that more anti-electrons were produced other than antiprotons.
Paul, what stopped the early inflation of the universe?
Well, since we don't know what started it, we certainly don't know what stopped it. The tradition in physics is if you don't understand something, give it a name. So some fundamental particle field of particles called inflatons, which at some point quit having an effect.
Are you making that up? Because it
No, I'm
sounds
not.
like it. It
They're
sounds
called inflatons.
like you might be.
Well, it sounds like something you might see on a weight loss commercial, but they actually did dub them inflatons.
How do we know that the gravitational constant and the speed of light constants are time invariant? And how do we know the universe is really uniform across
It's certainly
it?
not uniform, but G and C show up in ratios of forces. So we can look for changes in the effect of those forces over 13.8 billion years. And we don't see it.
Okay. From the chat, in the theory of the multiverse, there should be other universes
Yes.
currently in existence in parallel to us.
Yes.
Is there any thought on how to observe these?
Well, one set of theories says that dark matter is actually non-existent, and what we're doing is we're feeling the gravitational tug of an adjacent universe that we happen to be colliding with. Of course, the same people have other strange ideas.
So do we have any way of observing the possibility of a parallel universe? Or
Well, the idea here is that is the only way.
that is the only way?
Detect the gravitational pull. They're called branes, by the way, BRANES, like in membranes. So in a higher dimensional space-time, branes can approach each other or touch each other. Okay, just ask what happens if they touch each other. The answer is you might feel their gravity. That's the idea here. Well, I also want to say something. We talked about this in the last course I was involved with. The great scientist Haldane said in 1927, the universe is not only stranger than we imagine, it is stranger than we can imagine. So that should sort of be the first point of discussion. or God doesn't owe us an explanation.
So if the theory that there's the charge imbalance, if there were a charge imbalance, could that be a source of forces that we're not currently accounting for?
Well, here's the thing. We always first try to attribute something we see that's different from equilibrium to forces that we understand. A good example of this is that we and Andromeda and a lot of the galaxies in our vicinity are being drawn toward a great attractor that happens to be on the other side of the Milky Way, so we can't see it. But we judge from the motions of these galaxies and our own that there's something there attracting us. Right? At least we think there's something there attracting us because we see a departure from equilibrium. The answer may be it has to do with dark energy or dark matter. Or there could be actually a cluster of galaxies there we can't see. Part of the problem is we're limited in time and space for our observations. So we can't see the entire universe simultaneously. In fact, there's no possibility of seeing a good part of the universe.
How long does it take our galaxy to rotate so we could look that direction?
Well, one of the things we now understand about our galaxy and most galaxies are in a dynamic dance with each other. Within our local group, we have satellite galaxies, dwarf galaxies, and we also have evidence from star velocities within our own galaxy that we swallowed several of them over the last few billion years. So galaxies are certainly not in a dynamic equilibrium. And equilibrium is a starting point for many theories.
So Paul, the book suggests that photons lost energy as the universe expanded. So how does that mesh with the law of conservation of energy?
Well, what we get out of galaxies moving away from us at great distances is two different redshifts. The first one is the redshift due to the Doppler effect. But we also get another redshift that has to do with the gravitational well that the photons are coming out of. So one way of thinking about it, if you blow a balloon up, the expansion causes cooling. So photons shift to lower frequencies. The other point that is an interesting point about dark energy. Tyson discusses observations of cyanogen, CN. The excitation of CN depends on the temperature of its background radiation. So CN at large distances shows that the universe was indeed hotter there at the time that we observed the CN vibrations from. But the distant universe also was much denser. There should be a redshift associated with the light coming from distant regions that has to do with the fact the light is climbing an uphill battle against a denser region it starts in and the region we're in now. And that's not accounted for in the idea of dark energy.
Lila, you're muted.
Thank you. Hey, Paul, when you're referring to density, are you referring to the idea that as space-time expands, as space itself expands, then those light waves that are going to expand with it, so their wavelength lengthens and their
Yeah.
energy decreases.
Yes.
So-
The universe cools, basically.
So back to Nick's question, where does that leave us with the conservation of energy?
Well, there are several ways to think about it. Conservation of energy, when you expand a gas, is perfectly conserved. So the conservation of energy with the universe, what you've done is you've exchanged motion for a decline in energy for the photons coming back to you. If you think about it, a redshift due to expansion is actually the same thing as the temperature cooling down. The black body radiation we see coming from the most distant regions of the universe is actually, it's Doppler shifted because the universe is expanded, but the universe expansion also is equivalent to cooling. So the redder it gets, the cooler the object is that it's coming from. And they agree perfectly.
Thank you. So I think we want to take a minute here and shift a little bit to what Antha and I are calling faith questions or God talk.
Okay.
And one thing that was pointed out in the book is that the author of The Big Bang was actually a Belgian priest, considered the father of Big Bang cosmology.
Yes.
Copernicus was also a priest. And I'm thinking, well, that's interesting. And Antha, if you could pick up with some of the faith questions that you came up with, and maybe there is some others from everybody in our group.
All right, so one of the questions I had was that if we read Genesis, the author of Genesis didn't understand all this physics, and that our star was at least a third generation star and so forth. So there's a big gap in creation that's not covered in that work that was written a very long time ago. So I'm wondering if it were up to us now, and we wanted to write the story of creation, how would we write it so that, and so I'm tossing that out there for other people, what would we add? What would we do?
You're muted, Mike.
I'm thinking one big add is God is a lot more patient than we can imagine.
Yeah, maybe the word day is not that helpful. Maybe we should use the word eon, right?
Yeah, I think one big change would we wouldn't talk in terms of 7 days, possibly. We talk in terms of different terms.
Well, that's more allegorical. It's that if God exists out of space and time, who are we to say that it's presumptuous to say that an Earth day is a day for God when he made the whole universe?
Mike, I like to make a comment about the fact that a lot of scientific things were discovered by priests. If you go back through history over the last 400 or 500 years, it turns out that two groups of people made most of the scientific discoveries. They were either priests or noblemen, because they were the only ones that got the level of education that could allow them to make such things. Plus, they were independently wealthy in terms of being able to spend their time working on such subjects. So that's probably a lot of the reason that most of the people who made the discoveries were either noblemen or priests.
Well, I wanted to share with y'all my thoughts on expanding the creation story, which is I've been reading a book about the J source of the Old Testament or of Genesis, and that their project was connecting the nation of Israel with all people, with all creation. And it seems to me like that vision was actually too small, and that there's another couple of layers of connection that go deeper back, that we connect to not just our solar system, but the fact that we are made out of the products of earlier stars connects the solar system creation back to even earlier ones. And that, you know, if I were rewriting the Genesis creation story, I would definitely add some earlier layers and show how they were all created. And also that, yeah, the big thing I get out of the Genesis story, as I was telling Lila the other day, is that God made it and God said it was good. And I think that, you know, even going back the earlier steps, I would want that in there too.
Thanks, Antha. You know, I don't know a whole lot, but what is always great to hold up is that in sort of the rabbinic commentary, the first thing, according to Genesis 1, that's made is time, light and dark, not sun, moon, and stars, but light and dark, which allows there to be time. And that's kind of what Stephen Hawking says too, right? Like you have to go back to beginning of time, and physicists can't really speak about anything before time, right? And the book talks about these picoseconds, the Planck seconds, right? Which is sort of interesting. I think some people ask, like, well, what do physicists do? What do physicists do with, like, what happened before there was time?
Well,
that maybe is just a meaningless question. I don't know.
The idea of time in our universe is that it's part of space-time. If you have more than 4 dimensions, I have no idea how it shows up.
It might be interesting to try to figure out how a current version of Genesis would address the concept of the multiverse.
Yeah.
Well, we write narratives in science or religion based on what we understand in our everyday experiences. At the time most of the religious scripts and the original science was written, we thought that the universe revolved around the earth, that the laws for the heavens were different than the laws for the earth, and that the universe was very, very small at that time. We thought also that we didn't know about nuclear power. So the sun was a burning bunch of gas.
I could switch us to a different question, which is that with the Big Bang, and that it's, I think even with the multiverse, but that gives us a lot of room for God as creator as something outside of it. And there have been a number of times in human history where people of faith have believed a thing and have said, see, there's God. And then we've been wrong, and there have been big fights. And so what do we do if we can figure out the multiverse or something else that there's maybe makes less room for God? How do we handle that as people of faith?
I don't think just because we might grow in what we consider to be scientific understanding of the universe that really makes less room for God. I think, I just don't think there's a conflict there.
Well, science and religion should eventually reach the same conclusion.
Yeah, I would agree that I don't see a conflict. To me, as we discover more and understand better, we just appreciate the beauty more. And so it's one of the things that I always found the most amazing about Einstein was he came up with these radical thoughts, but they're expressed very simply in the math. The implications of that math are tremendous, but the equations he wrote are quite simple. And it's just beautiful to me. I find a beauty in that math. And that's what I'm looking forward. The next breakthrough is another thing that is beautiful in math, which has tremendous more applications. Right now, it seems like the math is just getting really complicated that people are using to explain things. And I'm looking for a simple math answer. Maybe that's too hopeful.
Well, I think right now we have a number of real paradoxes that clearly indicate we're not getting something. So that's basically where Einstein stepped in. Einstein was primarily a mathematician and a very good one. And so, like he said, if it looks like a duck, walks like a duck, sounds like a duck, assume it's a duck. And therefore, he sat down and wrote very simple equations that explain the null result on the Michelson-Morley experiment. And in the process, made major discoveries about the way space-time works. So we're anticipating the same sort of thing happening. When we finally run into enough dead ends, we decide, okay, we need to go in another direction. The search for dark matter has been going on very intensely for a long time, just like the search for ether did. So far, the results don't show any way out of the dilemma. And the longer we go without figuring out what dark matter is, the less likely it is that dark matter exists.
Paul, do you think that it's likely or possible, maybe not right, do you have a kind of a belief that eventually the math that answers these conundrums will be beautiful and not too complicated?
Well, as was pointed out, Einstein came up with a simple set of equations and simple assumptions, namely the speed of light is the same in all directions and in all frames. And so we could well find that there's something about gravity that can be written the same way.
So are we left with God is in quantum fluctuations? Is that what we're left with?
Say that again?
Are we left with the idea that God is in the quantum fluctuation that created the Big Bang? Is that what we're left with?
Well,
I wonder.
Einstein made a famous statement when it came to entanglement. He says, God does not play dice with the universe. And the response these days is, not only does he play dice with the universe, but he rolls the dice where you can't see them.
Mm. Are you referring to what's come out of the Large Hadron Collider?
No, I'm primarily referring to spooky accident at distance entanglement.
Yeah. So what Paul's talking about is, forgive me, Paul, and jump in if I don't get this right, but if you can take two particles, say two electrons that are spin paired, one up, one down, and separate them a great distance, miles, let's say miles, and ask one of them, are you spin up or spin down? And whereas it is in each electron is in a superposition state, both up and down at the same time. Once you inquire of one, are you up or down? It has to choose, if you will. And when it chooses, then the other one is constricted to then be spin down. And this happens at greater than the speed of light. And that's actually been observed. Is that what you're talking about, Paul?
Yes.
So that is very spooky action at a distance. And information does flow at faster than the speed of light. Can
Well,
you speak to that?
That's certainly one answer, but there may be other answers.
What are some of those other answers, Paul? And tell me, is it called spooky because it's faster than the speed of light, or just because it's like weird?
Well, the first response was that there are hidden local variables, that these electrons actually, when they are entangled, carry with them some information that says I'm up or down, or I'm going to be up or down. There's a theorem called Bell's theorem that makes that improbable, but that may not be the only answer. One answer is that there's Wheeler has mentioned this. There's a super time that the future actually already exists. And the interesting thing is the equations of physics work with time going forward or backward equally well. So there could be in the Uberverse or the multiverse some information that gets that spills over into ours that we have not yet figured out how to read. Again, going back to the statement that Tyson makes, the universe does not owe us to make sense to us. It has no obligation to make sense to us.
It's very exciting when we find stuff like this. Don't you think?
Yeah, the interesting thing is we believe as supposedly rational creatures that we will always find the explanation for everything we encounter. But again, we have no guarantee of that, either in the Bible, the Koran, or Tyson's book. The universe does not have an obligation to make sense to us. We'd like to think so, but maybe that's God's way of giving us humility.
Yeah, that's what I believe.
And yet it is deeply in our nature to try, I think.
Well, we have to try based on the assumption that logic and mathematics has gotten us this far. But that's not to say there isn't a limit. I'll talk about that later when I talk about intelligence and life in the universe.
Antha, next week we're gonna talk about dark matter and dark energy. And you've been reading a lot about this. The short version I have is supposedly we only understand about 5%, 4 or 5% of the universe is actually made of. The other 95, 96% is who knows? Antha?
Yep. So there's been a lot of physics going on over the last century, which is absolutely fascinating stuff, full of good stories of fascinating people and things that they've observed, like Paul was talking about Vera Rubin and the galaxies spinning and so forth, that they've got these ideas called dark matter and then they called dark energy because they had dark matter as a attempt at explaining. So I think next week we will continue forward with reading what Tyson has to say about that, and getting a lot of great stuff from Dr. Cloutier. Really appreciate you being here with us to help talk about all this stuff, because it's really interesting. And I hope
Thank you, Paul.
Thank
Right.
you.
Enjoyed it.
Thank you, Paul. Super, super grateful, and really looking forward to continuing our conversation next week.
Thank you.
In the meantime, if you have any other questions for Paul, you can always send them to Antha, Lila, or myself, and we can start next time Q&A with those questions. And keep in mind, what I love about Paul is that Paul's not offended by questions that, you know, maybe we don't understand everything. That's the beauty part of this. So if you say like, boy, I don't even understand what all this talk about protons is, don't be shy, because that's what Paul does super well, is brings us all up to speed. So have a great week, and any questions or follow-up, always grateful to receive.
Bye.